November 19, 1944, Yokosuka Naval Air Technical Arsenal, Japan. Commander Hiroshi Nakamura stood in the cavernous hangar, staring at the most beautiful enemy machine he had ever seen. The captured Vought F4U Corsair sat under harsh industrial lighting, its distinctive inverted gull wings casting shadows across the concrete floor like the wings of some mechanical raptor. The aircraft had belly landed near Kasumigura 3 weeks earlier, its pilot having misjudged his fuel reserves during a carrier strike. Japanese recovery teams had found it remarkably intact, propeller blades bent, but the massive Pratt Whitney R-2800 engine potentially salvageable. Nakamura had spent 15 years designing aircraft engines for the Imperial Japanese Navy. He had studied American engineering through intelligence reports and captured equipment, always searching for the technical secrets that gave enemy fighters their devastating performance advantage. But this machine represented something different. This was the aircraft American pilots called the Corsair, the fighter that Japanese pilots had learned to fear over the Solomons, the plane that could outrun, outclimb, and outgun nearly everything Japan could put in the air. And now it sat in his hangar, waiting to reveal its secrets. The numbers from initial inspection were staggering: 417 miles per hour maximum speed, 2,000 horsepower from a single engine, 650 caliber machine guns with enough ammunition to saw through a Zero's airframe in seconds. Everything about American military engineering seemed designed to overwhelm through sheer force, maximum capability, backed by unlimited industrial resources. But Nakamura knew that understanding enemy technology required more than admiring impressive specifications. He needed to discover why this machine performed as it did, and whether Japan could replicate or counter its advantages. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Lieutenant Commander Koji Watanabe, Yokosuka's senior test pilot, walked a slow circle around the Corsair, his experienced eyes cataloguing damage and assessing repair feasibility. The belly landing had been gentle, the aluminum skin showing scrapes and dents, but no structural failure. The propeller would need replacement, but the engine appeared intact from external inspection. Most remarkably, the fuel tanks had been nearly empty when the aircraft was recovered, suggesting the American pilot had attempted to nurse every last drop from his internal and drop tanks before accepting defeat. "We can make this fly," Watanabe said quietly, his voice carrying the confidence of someone who had coaxed damaged prototypes into the air countless times. "The airframe is sound. If the engine starts, we can test it." But even as he spoke, Nakamura felt the weight of Japan's industrial reality pressing against his enthusiasm. Making the Corsair fly would require solving problems that had nothing to do with engineering skill and everything to do with resources that no longer existed. The morning briefing brought together the technical team that would attempt to resurrect the captured fighter. Nakamura faced a semicircle of Japan's best aviation engineers, men who had designed the Zero's legendary maneuverability and created engines that squeezed maximum performance from minimal resources. But the expressions around the table reflected a growing awareness that Japan's war was being lost not in the air, but in the factories, refineries, and supply chains that fed military operations. Chief Engine Specialist Takeshi Yamada opened the Corsair's massive cowling, revealing the R-2800 double wasp in all its 18-cylinder complexity. The American engine dwarfed anything in Japan's inventory, 46 litres of displacement producing power that seemed almost wasteful in its abundance. Where Japanese engines had been designed to operate efficiently within carefully managed parameters, the R-2800 appeared built to generate overwhelming force regardless of fuel consumption or maintenance requirements. "The construction quality is extraordinary," Yamada reported, his hands moving over cooling fins that showed uniform precision across every cylinder. "Every component suggests manufacturing tolerances we cannot achieve with current production methods. The supercharger alone represents engineering sophistication beyond our capabilities." His assessment was clinical, absent the bitterness that might have colored such observations earlier in the war. By November 1944, Japanese engineers had learned to separate technical admiration from strategic despair. But it was fuel systems specialist Kenji Tanaka who identified the problem that would define every subsequent decision about the captured Corsair. Tanaka had spent the previous week analyzing the aircraft's fuel system documentation, studying the maintenance manual recovered from the pilot's survival kit, and calculating the thermodynamic requirements of the R-2800's high-compression cylinders. "The engine requires minimum 100-octane aviation gasoline," he announced, his voice carrying the finality of a death sentence. "The manual specifies 130 octane for maximum performance operations, with water methanol injection for emergency power. Our current production fuel is 87 octane. By next month, we may be mixing pine root oil to stretch supplies, which will lower octane to 85. The silence that followed Tanaka's assessment lasted perhaps 10 seconds, but in that brief moment, Nakamura understood that the beautiful machine in his hangar represented not just American engineering superiority, but the fundamental impossibility of Japan's strategic position. Commander Nakamura had joined the Navy's technical branch in 1929, during an era when Japanese aviation was still learning from foreign expertise. He had studied American engine design through licensed manufacturing agreements, watching as Pratt Whitney's radial engines powered both American and Japanese aircraft through the 1930s. The relationship had been cordial, even collaborative, with American companies willingly sharing technology in exchange for licensing fees. But that cooperative era ended with the embargo, when the United States cut off oil exports in July 1941. Japan lost access not just to crude petroleum, but to the entire infrastructure of American refining technology. The high-octane aviation gasoline that American engines were designed to consume required catalytic cracking facilities, isomerization units, and tetraethyl lead production that Japan had never developed domestically. American aviation fuel was manufactured to exacting specifications, blended from multiple refinery streams, and tested using standardized engines that ensured consistent performance across millions of gallons of production. Japan's fuel production told a different story entirely. Even before the war, Japanese refineries had struggled to meet aviation fuel demands. The octane ratings achieved through domestic production topped out around 92 for Navy aircraft, with Army aviation typically using 87 octane. These numbers reflected not inferior engineering, but the brutal mathematics of resource scarcity. Japan's entire 1942 aluminum production totaled 18,000 tons. That same quantity represented approximately 3 weeks of American aircraft industry consumption alone. The fuel crisis went deeper than simple octane numbers. Lieutenant Tanaka's detailed analysis revealed that American aviation gasoline contained carefully balanced aromatic hydrocarbons, additives that prevented vapor lock at altitude, anti-icing compounds, and stability enhancers that allowed long-term storage without degradation. Japanese fuel production could match none of these characteristics consistently. The synthetic fuel program, modeled after German Fischer-Tropsch technology, produced gasoline with base octane around 80, but required enormous industrial infrastructure to operate. By November 1944, Japan's synthetic fuel production was collapsing under Allied bombing. The refineries in Palembang, captured from the Dutch in 1942 and providing Japan's only significant source of high-grade petroleum, were being systematically destroyed by B-29 raids. Tanker shipping from the East Indies faced submarine interdiction that had reduced deliveries to a fraction of pre-war levels. The pine root oil program, desperate measure though it was, represented Japan's attempt to keep aircraft flying on any combustible liquid that could be coaxed from natural resources. Nakamura reviewed captured American fuel specifications with growing comprehension out of the technological gap his team faced. The R-2800 engine achieved its remarkable power through compression ratios that required knock-resistant fuel to prevent premature detonation. When an engine designed for 130-octane fuel attempted to run on 87 octane, the result was predictable. The fuel-air mixture would detonate before the piston reached top dead center, creating shock waves that pounded bearings, cracked cylinder heads, and generated heat that rapidly exceeded cooling system capacity. The thermodynamics were unforgiving. Each increase in octane rating allowed higher compression ratios, which translated directly into greater power output from the same displacement. American engines running on 130-octane fuel could extract nearly 50 kilowatts per liter, performance that Japanese engines could never match with available fuel. But the relationship was not linear. Running a high-compression engine on inadequate fuel didn't simply reduce power. It destroyed the engine through detonation that American pilots called knocking, and Japanese engineers recognized as a death sentence for precision machinery. Intelligence reports from the previous 2 years documented Japan's growing awareness of the fuel crisis. Captured American aircraft, when tested with Japanese fuel, exhibited severe engine problems. A P-38 Lightning recovered in New Guinea had suffered catastrophic engine failure after 12 minutes of ground testing on 87-octane fuel. The pilot's manual specified 100-octane minimum, but desperation had prompted the test anyway. The results confirmed what Japanese engineers already understood. American aircraft were optimized for a war of abundance, designed without consideration for fuel constraints that defined Japanese operations. The captured Corsair represented the ultimate expression of this philosophy. Its R-2800 engine had been designed in 1937, when American fuel technology was already producing 100-octane aviation gasoline commercially. By 1944, American combat aircraft routinely used 130-octane, with water injection allowing emergency power settings that would have seemed impossible just 5 years earlier. The entire American approach to aviation assumed unlimited access to the world's most sophisticated fuel refining infrastructure. Nakamura understood that even if his team could somehow acquire sufficient high-octane fuel for testing, the knowledge gained would be largely useless. Japan lacked the industrial capacity to build R-2800 equivalent engines, lacked the refining infrastructure to produce appropriate fuel, and lacked the aluminium supplies to manufacture aircraft in sufficient quantities to matter strategically. The Corsair was a magnificent engineering achievement, but it was also a machine that could only exist within an economic system Japan could never replicate. The parallel stories of engine development revealed how completely different resource bases had shaped engineering philosophy. Pratt Whitney's path to the R-2800 began with unlimited access to high-grade aluminum, chromium molybdenum steel, and precision manufacturing equipment. American engineers could specify materials based purely on performance requirements, knowing that procurement would find or develop whatever was needed. The R-2800's 18 cylinders required thousands of components manufactured to tolerances measured in thousandths of an inch, assembled by workers using specialized tools and testing equipment that Japanese factories could not duplicate. Japanese engine development followed constraints that American designers never faced. The Nakajima Sakai engine that powered the Zero achieved its remarkable efficiency through careful optimization around available materials and fuel. Its 14 cylinders produced 1,000 horsepower on 92-octane fuel, performance that reflected brilliant engineering within severe limitations. When American pilots praised the Zero's maneuverability and range, they were unknowingly admiring Japan's success at extracting maximum capability from minimal resources. But by 1944, the strategic context had shifted in ways that made Japanese engineering achievements irrelevant. The Corsair's 2,000 horsepower overwhelmed the Zero's maneuverability through simple force. American pilots no longer needed to dogfight with skill and patience. They could use speed and power to dictate engagement terms. The fuel that made this performance possible was being produced in quantities Japan could not match, refined to specifications Japan could not achieve, and consumed at rates that would have bankrupted Japan's entire petroleum reserve in weeks. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The decision about Whether to attempt flying the captured Corsair crystallized around a simple calculation of risk versus benefit. Nakamura's team could cannibalize parts from crashed Japanese fighters to replace the Corsair's bent propeller, could fabricate mounts and connections to adapt systems, could even acquire enough high-octane fuel for perhaps one test flight by diverting supplies from experimental programs. But what would such a test prove beyond what they already knew? Lieutenant Watanabe argued for the flight test with the passion of a pilot who had spent 4 years watching American aircraft outperform Japanese fighters in every measurable category. "We need to understand how it flies," he insisted during a late November meeting. "The performance numbers tell us what it can do, but only flight testing reveals how it does it. Maybe there are handling characteristics we can exploit. Maybe the controls are less responsive than specifications suggest. Maybe high-speed maneuvering reveals structural limits." Yamada, the engine specialist, opposed the test with equal conviction. "We know how it flies," he responded quietly. "It flies like an aircraft with 2,000 horsepower and unlimited fuel. We know the airframe is robust. We know the controls are power-assisted. We know it can sustain damage that would destroy a Zero. Testing it on inadequate fuel will prove only that engines designed for 130 octane gasoline cannot run on 87 octane. We already know this." The debate revealed deeper questions about Japan's position in late 1944. Every resource diverted to testing captured enemy equipment was a resource unavailable for defending against B-29 raids that were systematically destroying what remained of Japanese industrial capacity. The high-octane fuel required for even a brief test flight represented enough aviation gasoline to keep multiple Japanese fighters operational for weeks. The engineering man-hours spent on the Corsair project could be directed toward improving production aircraft or developing defensive systems. Nakamura listened to both arguments before rendering his decision. "We will conduct limited ground testing only," he announced. "We will start the engine using the highest octane fuel available, run it at minimal power settings, and document its operation for intelligence purposes. We will not attempt flight testing. The risks outweigh potential benefits, and we cannot spare the fuel." His choice reflected the pragmatism that had come to dominate Japanese military thinking as the war situation deteriorated. The ground test preparations consumed 2 weeks of careful work. Mechanics fabricated a new propeller by modifying blades from a damaged Japanese bomber, machining the hub to match the Corsair's shaft specifications. Electrical systems required adaptation to Japanese ground power equipment, a process that revealed the sophistication of American avionics. Most challenging was acquiring fuel. Nakamura obtained 30 gallons of 92 octane through official channels, then discreetly arranged for another 10 gallons of 95 octane experimental fuel from a program developing high-compression engines for interceptor prototypes. Lieutenant Tanaka calculated that mixing the two supplies would yield approximately 40 gallons of 93 octane, still far below the engine's requirements, but perhaps adequate for brief low-power operation. The fuel would be contaminated slightly by storage in tanks designed for lower-grade gasoline, but careful filtering might reduce problems. Every calculation carried qualifications and approximations because the team was attempting something for which no procedures existed, running an engine designed for resources they did not possess. December 12, 1944, dawned cold and clear over Yokosuka. The Corsair had been positioned on the test apron, its propeller installed, fuel tanks filled with a precious mixture that represented weeks of scrounging and negotiation. Nakamura stood beside the aircraft with his core team, each man aware they were attempting something that might provide valuable intelligence or might simply confirm what they already suspected. Watanabe climbed into the cockpit, his smaller stature immediately apparent in a space designed for larger American pilots. The pilot's seat was too far back, the controls positioned for arms longer than his, but the gauges were comprehensible, the ignition sequence documented in the captured manual, the basic layout familiar from intelligence briefings. He verified that fuel selectors were properly set, that mixture controls were in the start position, that everything matched the checklist procedures. The R-2800 turned over slowly as ground crew engaged the starter, 18 cylinders compressing fuel-air mixture in sequence. On the third attempt, the first cylinder fired, then another, and suddenly the massive engine was running, its deep mechanical growl filling the test apron with sound that was simultaneously impressive and ominous. Watanabe monitored gauges carefully, watching as oil pressure climbed toward normal range and cylinder head temperatures began their inevitable rise. For the first 2 minutes, the engine ran smoothly. The team watched in fascination as American engineering performed exactly as designed, precision machinery operating within acceptable parameters, despite fuel that fell short of specifications. Yamada noted the coolant temperatures climbing slightly faster than manual specifications indicated, but nothing suggesting immediate problems. The exhaust smoke was darker than expected, indicating incomplete combustion, but the engine continued running steadily at idle power. At minute 3, the first indication of trouble appeared. A metallic rattling from deep within the engine, barely audible over the exhaust note but instantly recognizable to experienced engineers. Detonation. The inadequate octane fuel was igniting prematurely in one or more cylinders, creating shock waves that hammered pistons and bearings. Watanabe reduced power slightly, but the knocking intensified rather than diminished. By minute 5, multiple cylinders were detonating. The cylinder head temperature gauges showed readings climbing into dangerous territory, far exceeding normal operating limits. The cooling system, designed for fuel that burned smoothly and controllably, could not dissipate the excessive heat generated by premature ignition. Yamada made quick calculations, recognizing that thermal stresses were approaching levels that would cause permanent damage. At minute 8, Watanabe saw the oil temperature gauge climbing past red line limits. The engine oil, subjected to temperatures beyond its thermal stability range, was breaking down and losing its lubricating properties. Bearings designed for smooth operation under controlled loads were being pounded by detonation shock waves while starved of adequate lubrication. The combination was catastrophic for precision machinery. "Shut it down," Nakamura ordered at minute 9. Watanabe pulled the mixture control to idle cutoff, starving the engine of fuel. The R-2800 died with a final cough of dark smoke, its 18 cylinders falling silent after operating for exactly 9 minutes and 43 seconds. The test had lasted long enough to prove what everyone already knew. An engine designed for 130 octane fuel could not survive on 93 octane, even at minimal power settings. The post-test inspection revealed damage that confirmed the inevitability of failure. 2 cylinders showed scoring on piston walls, where excessive heat had broken down the oil film that normally provided lubrication. 3 cylinder heads exhibited cracks radiating from spark plug bosses, thermal stress fractures caused by temperatures far exceeding design limits. The supercharger bearings showed metal transfer, the beginning stages of seizure that would have destroyed the entire assembly within another 5 minutes of operation. Most tellingly, when Yamada removed and examined the spark plugs, several showed ceramic insulators fractured by detonation shock waves. The plugs had been manufactured to extraordinarily high standards, but no amount of manufacturing quality could protect components from the physical forces generated when fuel detonated prematurely in a high-compression cylinder. The American engine had failed not because of inferior design, but because it was being asked to operate outside the parameters for which it had been created. Nakamura drafted his final report on December 15th, 3 days after the failed test. His assessment was brutally honest about the implications of what they had learned. The Corsair represented engineering that Japan could admire but never replicate, not because Japanese engineers lacked skill, but because they lacked the industrial infrastructure that made such engineering possible. The F4U Corsair embodies the American approach to warfare through overwhelming industrial capacity, he wrote. Every aspect of the aircraft's design assumes unlimited access to high-octane fuel, precision manufacturing, and replacement resources. The aircraft cannot operate effectively without the industrial system that created it. Japan's captured Corsair is operationally useless, not because we lack skilled pilots or mechanics, but because we lack the petroleum refining technology that enables its engine to function. The broader implications of the Corsair investigation haunted Nakamura through the winter of 1944 and into 1945. Japan had built brilliant aircraft that optimized performance within severe resource constraints. The Zero, the Hayabusa, the Oscar, all represented engineering excellence that Western designers had initially underestimated. But as American industrial power fully mobilized, Japanese engineering advantages evaporated before machines that didn't need to conserve fuel or minimize manufacturing complexity. The captured Corsair sat in Yokosuka's hangar through the spring of 1945, a monument to technological superiority that Japan could study but never match. When American forces occupied Yokosuka in August, they found the aircraft essentially intact, its engine damaged from one brief test, but its airframe preserved. American intelligence officers photographed the Corsair, surrounded by Japanese engineers' meticulous documentation, evidence of a technical analysis program that had understood exactly why Japan was losing the war. Lieutenant Commander Watanabe, interviewed by American technical teams after the surrender, provided insight into Japanese thinking about captured enemy equipment. "We knew American aircraft were superior," he explained through an interpreter. "We understood that your fuel, your aluminum, your manufacturing capacity gave you advantages we could never overcome. The Corsair test simply confirmed what we already knew. You had built an aircraft that required industrial resources we did not possess. In that sense, every captured American aircraft was a reminder not of our engineering failures, but of our strategic impossibility." The fuel crisis that prevented Japan from testing the Corsair effectively had grown worse through the final months of the war. By April 1945, Japanese aviation gasoline production had collapsed to the point where training flights were severely restricted. The Pine Root oil program, despite mobilizing thousands of workers to collect and process raw materials, never produced fuel in sufficient quantities or quality to matter. New pilots received minimal flight training, experienced pilots hoarded fuel like gold, and aircraft sat grounded, not from lack of machines, but from lack of fuel to operate them. American bomber crews, attacking Japanese airfields in the summer of 1945, reported finding dozens of intact aircraft that never took off to intercept the raids. Post-war analysis revealed these aircraft were fully functional, their engines properly maintained, their pilots available and trained. They remained on the ground because fuel did not exist to put them in the air. The Corsair's test had predicted this outcome months earlier. Japan had built an aviation force that could no longer function because the industrial resources required to support that force had been systematically destroyed. The R-2800 engine from Yokosuka's captured Corsair was eventually transported to the United States for detailed engineering analysis. American engineers studying the Japanese test documentation found the technical analysis impressively thorough, the failure predictions accurate, the understanding of fuel chemistry and thermodynamics sophisticated. Japanese engineers had not failed to comprehend American technology. They had simply lacked the industrial capacity to replicate it. Commander Nakamura survived the war and later contributed to Japan's post-war aviation industry recovery. In interviews conducted during the 1960s, he reflected on the Corsair test as a defining moment in his understanding of modern warfare. "We were fighting two different wars," he observed. "The Americans fought with unlimited resources, designing equipment for maximum capability without concern for fuel consumption or manufacturing complexity. We fought with severe constraints, optimizing every design for minimal resource usage. Both approaches made sense within their contexts, but when those contexts collided, the side with greater industrial capacity would inevitably prevail." The lesson of the captured Corsair extended beyond fuel and engines to fundamental questions about technology and war. Superior engineering could not overcome inferior resources. Brilliant design could not substitute for manufacturing capacity. Individual Japanese aircraft might match or exceed American counterparts in specific performance categories, But those achievements became irrelevant when American factories produced 10 aircraft for every Japanese one, when American refineries supplied unlimited fuel while Japanese supplies dwindled to nothing. Commander Nakamura survived the war and later contributed to Japan's post-war aviation industry recovery. In interviews conducted during the 1960s, he reflected on the Corsair test as a defining moment in his understanding of modern warfare. "We were fighting two different wars," he observed. "The Americans fought with unlimited resources, designing equipment for maximum capability without concern for fuel consumption or manufacturing complexity. We fought with severe constraints, optimizing every design for minimal resource usage. Both approaches made sense within their contexts. But when those contexts collided, the side with greater industrial capacity would inevitably prevail." The captured American pilot, Lieutenant Robert Henderson of VF-84, provided his own perspective on the incident when questioned after his recovery from internment in 1945. Henderson had been flying a combat air patrol mission from USS Bunker Hill when navigation errors and aggressive maneuvering during an engagement left him critically low on fuel over hostile territory. His decision to attempt a belly landing rather than bail out over water had inadvertently given Japan one of the most intact Corsairs they would capture during the war. "I knew the aircraft was too valuable to simply abandon," Henderson later explained in debriefing reports. "We'd been briefed that the Japanese were desperate to understand our technology. I tried to set it down as gently as possible while destroying the IFF equipment and radio codes. But there wasn't time to damage the engine or fuel system documentation before Japanese soldiers arrived." His capture had been swift and professional, with Japanese recovery teams reaching the crash site within hours. Henderson spent the remaining months of the war in a prisoner facility near Tokyo, unaware that the aircraft he'd flown had become the subject of intensive technical analysis. During his interrogation, Japanese intelligence officers questioned him extensively about the Corsair's performance characteristics, fuel requirements, and maintenance procedures. Henderson provided only basic information permitted under the Geneva Convention, but his interrogators already possessed detailed technical manuals recovered from his aircraft. The interrogation sessions revealed how desperately Japan sought intelligence about American aviation technology. One Japanese officer, speaking surprisingly good English, had asked Henderson detailed questions about fuel octane ratings, water injection systems, and combat radius calculations. Henderson realized these were engineers, rather than typical military interrogators, men genuinely trying to understand technical rather than tactical information. "They showed me photographs of the Corsair in their hangar," Henderson recalled. "The aircraft looked almost undamaged except for the propeller. One of the engineers, speaking through an interpreter, asked if I knew what octane fuel the R-2800 required. I told him it was in the manual they'd already captured. He said they knew the specifications but wanted to understand if pilots ever operated on lower octane fuel in emergencies. I explained that we never faced fuel shortages, that we always had more than enough high-octane aviation gasoline wherever we operated." This exchange had apparently depressed the Japanese engineers considerably. Henderson remembered the interpreter's face falling as he translated this information, the confirmation that American forces operated with fuel abundance that Japan could not imagine. The interrogation ended shortly afterward, with the engineers thanking Henderson politely for his time before guards returned him to his cell. The fuel infrastructure that supported American operations in the Pacific represented logistical achievement, rivaling any combat victory. By late 1944, the U.S. Navy had developed a complete mobile refueling system that could establish forward fuel depots on newly captured islands within weeks. Tanker ships designed specifically for rapid fuel transfer could pump thousands of gallons per hour through flexible hoses to shore-based storage tanks. These tanks, fabricated in sections and transported on cargo ships, could be assembled quickly by construction battalions. At Ulithi Atoll, captured in September 1944, American engineers constructed a fuel depot capable of storing over 8 million gallons of aviation gasoline within 2 months. The facility included pumping stations, filtration equipment, and distribution pipelines connecting to multiple anchorages where ships could refuel at sea. Similar installations appeared at Eniwetok, Saipan, and Guam, each serving as nodes in a vast petroleum distribution network spanning the Pacific. The quality control measures surrounding this fuel infrastructure were equally impressive. Every batch of aviation gasoline underwent testing before being loaded on tankers in California. Samples were retested upon arrival at forward depots to ensure no degradation during transport. Mobile testing laboratories accompanied fuel shipments, equipped with portable octane testing apparatus and contamination detection equipment. American aircraft commanders could rely absolutely on fuel quality, knowing that every gallon met the same specifications, whether pumped in San Diego or Okinawa. Japanese intelligence had documented this logistical superiority through prisoner interrogations, captured documents, and aerial reconnaissance of American facilities. Reports reaching Tokyo painted a picture of fuel abundance that seemed almost fantastical to commanders, struggling with severe shortages. One intelligence assessment from March 1945 noted, American forward bases possess fuel storage exceeding Japan's entire strategic reserve. Their tanker fleet tonnage equals our total remaining merchant shipping. They have created a petroleum supply system we cannot disrupt through any available means. This recognition of futility permeated Japanese military thinking in the war's final months. If Japan could not fly its aircraft for lack of fuel, what purpose did technical analysis of captured American aircraft serve? Yet the work continued at Yokosuka and other research facilities, partly from institutional momentum, partly from genuine desire to understand the industrial methods that had produced such overwhelming superiority. Engineer Yamada, the engine specialist who had predicted the Corsair test's failure, spent considerable time analyzing the R-2800's construction details even after the engine was damaged beyond repair. His technical report, completed in February 1945, documented manufacturing techniques that Japanese industry could not replicate even if all resource constraints were removed. The precision forging of connecting rods required die sets costing more than Japan spent annually on all engine tooling. The cylinder barrel manufacturing process used broaching machines that didn't exist in Japanese factories. The supercharger impeller casting technique demanded foundry temperature controls beyond Japanese capabilities. Every component tells the same story, Yamada wrote in his conclusions. American manufacturing represents not just greater scale but fundamentally different approaches to production. They manufacture components to tolerances we reserve for hand-fitted racing engines, then assemble these components into production engines, using methods we would consider experimental. The industrial base supporting this manufacturing capability exceeds our entire industrial economy by factors we cannot calculate accurately. These assessments circulated among Japanese aviation leadership, contributing to growing recognition that continuing the war served no strategic purpose. If Japan's engineers, among the most skilled in the world, concluded that American industrial superiority was insurmountable, what hope remained for military victory? The Corsair analysis became one more data point in calculations that would eventually lead to surrender, though it would take atomic bombs and Soviet intervention to force that final decision. The psychological impact on Japanese pilots who faced Corsairs in combat was profound and became worse as fuel shortages reduced training opportunities. Flight Petty Officer Saburo Sakai, one of Japan's highest-scoring aces, encountered Corsairs during operations over Iwo Jima and later wrote about the experience. The Corsair pilots didn't need exceptional skill because their aircraft gave them every advantage, he observed. They could choose when to engage, could dive away when threatened, could climb faster than we could follow. Our only hope was catching them in vulnerable positions, but their radios allowed them to coordinate so such opportunities rarely occurred. Sakai's assessment matched intelligence analysis, showing that by 1945, American fighter doctrine emphasized using superior performance rather than dogfighting skill. Corsair pilots were trained to avoid turning engagements with Japanese fighters, instead using boom and zoom tactics that exploited their speed and climb rate advantages. The 2,000 horsepower that Japanese engineers couldn't replicate translated directly into tactical dominance that Japanese pilots couldn't overcome through skill or courage. The fuel disparity affected combat outcomes in ways beyond simple aircraft performance. American fighters could afford to patrol aggressively, burning fuel freely while searching for targets. Japanese fighters had to conserve fuel carefully, limiting patrol times and reducing combat effectiveness. When engagements occurred, American pilots could use water injection and maximum power settings without concern for fuel consumption. Japanese pilots operated at reduced power settings to extend range, accepting performance penalties that made them easier targets. These tactical constraints were well understood at Yokosuka, where Nakamura's team analyzed combat reports alongside technical intelligence. The connection between fuel availability and combat effectiveness was direct and quantifiable. Japanese pilots reported that American fighters seemed to always have altitude and speed advantages when engagements began, advantages that reflected the ability to patrol at full power, while Japanese fighters climbed slowly on reduced power settings to conserve fuel. Lieutenant Watanabe, who had tested the Corsair engine, later flew combat missions defending Tokyo against B-29 raids. His experience illustrated how incompletely fuel constraints had crippled Japanese air defense. "We would receive radar warning of incoming bombers with perhaps 30 minutes' notice," he recalled. But starting engines, warming them properly, and climbing to intercept altitude consumed so much fuel that we often had only minutes of combat time before needing to return to base. If we missed the bombers on first pass, we lacked fuel for a second attempt. These operational limitations meant that Japan's fighter force, even when aircraft were available, could not effectively defend against American bombing. The same fuel crisis that prevented testing captured Corsairs properly also prevented Japanese fighters from intercepting the bombers, destroying Japan's cities. The strategic situation had become circular. Lack of fuel prevented effective air defense, which allowed bombing of fuel production facilities, which further reduced fuel availability. The Pine Root Oil Program's failure exemplified Japan's desperation. Despite mobilizing over 100,000 workers to collect pine roots and stumps, total production never exceeded a few thousand barrels monthly. The fuel quality was so poor that engines often suffered damage after just 10 hours of operation. Maintenance crews reported that spark plugs had to be cleaned after every flight, that fuel filters clogged repeatedly, that carburetors gummed up with deposits that required complete disassembly to remove. Technical specialist Kobayashi, assigned to evaluate pine root oil's suitability for aviation use, submitted brutally honest assessments throughout spring 1945. This material should not be considered aviation fuel by any standard definition, one report stated. Its octane rating of approximately 70 to 75 makes it unsuitable for any aircraft engine designed after 1930. The impurity content causes accelerated wear that reduces engine service life by an estimated 70%. Use should be restricted to ground equipment and only when no alternative exists. These reports were ignored or suppressed because acknowledging pine root oil's uselessness would have meant admitting that Japan's Air Force was completely grounded. Instead, official directives continued requiring its use, with predictable results. Accident rates increased as engines failed unexpectedly. Combat effectiveness declined as pilots struggled with rough-running engines. Maintenance workload multiplied as fuel system components required constant servicing. The captured Corsair, sitting silently in Yokosuka's hangar, served as daily reminder of what proper fuel could accomplish and what its absence prevented. The aircraft became almost symbolic for Japanese engineers, representing technical excellence rendered useless by resource constraints. Some engineers would visit the hangar during off hours, studying the machine that their fuel supplies could not support, contemplating the industrial disparity that made victory impossible. When American occupation forces arrived at Yokosuka in September 1945, they found comprehensive documentation of the Corsair analysis. The reports were translated and forwarded to U.S. technical intelligence, where analysts marveled at their thoroughness and accuracy. One American engineer noted, "The Japanese understood every technical aspect of why the Corsair was superior. They correctly identified fuel as the critical limiting factor. Their analysis was professionally executed, and their conclusions were sound. They simply lacked the industrial resources to act on this knowledge." The Corsair itself was eventually shipped to the United States for display, its damaged engine preserved as evidence of Japan's final attempts to understand American technology. The aircraft became part of the Smithsonian collection, where it remained as testimony to the industrial war that determined the Pacific conflict's outcome. Visitors seeing the plane rarely understood that its greatest significance lay not in its combat record, but in what it revealed about resource disparities that no amount of engineering skill could overcome. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.